Hello, my name is Laita Diaro, and this is the Physics 2212 Lab 1, which is about charged tapes. So the contents of this video are starting off with an introduction, introducing some of the formulas and principles we're going to be using for this experiment. Then we're going to go on to a description of the experiment and some footage from it. Then we're going to make a computational model using GlowScript to find actual values from our experiment. And then lastly, we're going to do some analysis and answering what if and why questions. So to start off, the introduction. The key ideas at play are Newton's second law, which is F equals ma, and also Coulomb's law. And the results of the experiment are that the positive charges on both tapes cause repulsion to one another and attraction to other objects. The electric charge on one of the tapes is around 4.85 times 10 to the 9 coulombs, and the tape is deficient by around 3.029 times 10 to the 10 electrons. The initial conditions are the mass of the tape is around 1.5 times 10 to the negative 4 kilograms, which we found by multiplying the length of the tape times the approximate mass per length, which is about 1 gram per meter. The length of the strips used is about 0.5 meters or 15 centimeters, and the width is about 2 centimeters. This is a little diagram showing how two pieces of tape might interact and what they look like side by side. So the system is tape B on the top, and the surrounding would be tape A, which is fixated, and the guiding formulas are up here. So these are the force generated by electrons and the electric fields. So to set up this experiment, we start off with putting a piece of tape on the table, and that will be the base piece, and then layering on two pieces of tape on top of them, and we rapidly peel the tapes off in order to generate a charge. So my hypothesis of what I thought would happen is that the tape would attract or repel my hand depending on the way I switch the side. So to test this theory, I held the charged tapes close to my hand and to other objects. I observed that the tape attracted to my hand and to other neutral objects regardless of which way it faced, but it repelled from itself. This means that the tapes both have a like charge that's opposite to all other objects. Since most other neutral objects are slightly negative, the rapid ripping off of the tape would intuitively leave behind some electrons, and that means the tapes would be a positive charge. And this is also proved by our GlowScript model. So this is a short video of the experiment. So as you can see, this is me ripping the tape off, and in the next video we can see how the tape reacts. So it's trying to stick to the desk at first, and when pulled up it also sticks to my finger. And we can see here it's a little demonstration of me with another tape, and it's attracted to my finger, and I calculated that distance was around 2 centimeters. So we're going to put this into the computational model, and this is the Python code that I used. So for the first model, we had to find the charge of a single strip. So going through, those are all the constants, and you can see that we have the Coulomb's constant, the mass of the tape, length, width, the force of gravity, which is the gravitational force of the tape, and we added that onto the electrical force in order to make up for that to stay consistent. And this is the formula of the electric field around the tape. And we are assuming in this calculation that the tape is a point charge and that it's evenly distributed. So the program found that it's about 4.85 times 10 to the 9 coulombs. So the second computation is this code, and we still have the gravitational and Coulomb's constants, as well as the mass and the charge that we found with the previous program, and we again have the electric field using both the observational location and the charge. All of this is code for the computer model, and if we run this program, we can see that this is the force that is found. So some observations. We did calculate a loss of electrons. We calculated a loss of electrons by using the n equals q over e formula, and we know that the charge of a singular strip is 4.85 times 10 to the negative 9, and this is the charge of a single electron. So if we divide that, we find that the electron loss is 3.029 times 10 power 10. And there is possible error from loss of charge after handling the tape, and also we don't know the specific charges of the neutral surfaces, so we just assume them to be neutral. That could also be another point of error. And another thing, in my computer model, it showed a slight attraction rather than a repulsion, and I can probably chalk that up to an error in measuring the distance, because it's a very slight attraction where it should have been a repulsion. So some of the assumptions that we made is that the tape has an evenly distributed charge and that both the U-tapes have the same amount of charge. The other objects in the base tape are a point charge, which they aren't, but we assume that they are, and we also ignored the air resistance. So this may have affected our calculations because the charges are not necessarily same on the two tapes, and they aren't concentrated, and the length of the tapes may differ. So there is a couple things that might have affected the calculation, but the bigger thing is air resistance. We only took the electric force and gravitational force into account, and air resistance is a big force on the tape because it has a low mass compared to the surface area, so it will have a higher drag. So air resistance should have been calculated, although it would have been hard to include in this simulation. So for the what if and why questions. If the electrons and protons had opposite charges, what would I change about the observations, and why is it important to handle the tapes as little as possible? So for the what if questions, it honestly would not change much. It would just change the sign of our charges because the proton and electron have an equal but opposite charge value, and the calculations would pretty much stay the same apart from the sign differences. It's important to handle the tapes as minimally as possible because charges will try to neutralize and they will transfer through surface contact, especially through conductors, and human skin is a rapid conductor, so that will tamper with experiment results. Thank you, and peace out.